The idea that Earth held a pivotal role in cosmic events was challenged by the Andromeda Galaxy, which significantly altered our understanding of the cosmos. That moment proved that there are innumerable more galaxies scattered over the vastness of space, in addition to our own, the Milky Way. Technological developments and observation have made it possible for us to look farther into space and solve the secrets of Andromeda, especially with the installation of devices such as the James Webb Space Telescope. But new discoveries based on information obtained by the James Webb Telescope have challenged a lot of long-held notions about this nearby galaxy. The Milky Way was often perceived more than a century ago as a thin, diffused bar of light spanning the night sky. This view, shaped by the primitive technology of the era, made it more difficult for astronomers to identify individual stars in our galaxy. Nevertheless, a number of beliefs endured. Most of them linked the Milky Way to the center of creation, the point at which the heavenly and terrestrial domains met. Our understanding of the Milky Way did not undergo a radical change until the 17th century, thanks to Galileo Galilei's groundbreaking telescope research. Galileo's discoveries showed that the Milky Way is a vast collection of stars, planets, and other celestial bodies scattered throughout space, not just a strip of light. Building on Galileo's discoveries, Thomas Wright postulated a revolutionary theory in the 18th century, arguing that the Milky Way was actually a flattened disk with our solar system snuggled within of it, rather than a random constellation. But Edwin Hubble's findings from the early 20th century were what really altered our understanding of the cosmos. Hubble discovered far-off nebulae outside the Milky Way and proved they were unique galaxies by using the 100-inch Hooker telescope at the Mount Wilson Observatory. The Andromeda Galaxy, M31, one of the closest to our own, was among these galaxies. The Persian scientist Abd al-Rahman al-Sufi first characterized Andromeda as a tiny cloud in the 10th century, marking the beginning of records of the planet's existence. Because there were no telescopic tools available, al-Sufi's excellent observational abilities helped him recognize Andromeda as a distinct celestial body among the usual stars scattered over the night sky. After Simon Marius published a more thorough description of Andromeda in 1612, based on telescopic observations, detailed observations of the planet really got underway. Charles Messier later catalogued Andromeda as M31 in 1764, mistakenly crediting Marius alone for its discovery and ignoring al-Sufi's prior identification. In 1864, Andromeda's nature was further clarified by the landmark discoveries made by English astronomer William Huggins, which marked a significant advancement in our understanding of the galaxy. With each new astronomer, the amount of knowledge about Andromeda grew, allowing for a more complex understanding of the planet's makeup, structure, and location in the universe. Huggins's revolutionary studies of Andromeda's spectrum, which revealed that the galaxy's spectral signature was different from that of a normal gaseous nebula, were a turning point in our understanding of this galaxy and opened the door to further research into Andromeda's real nature. Even with its enormous size, Andromeda's mass is thought to be between 1 and 2 trillion times that of our Sun. For millennia, scientists have been fascinated by this massive cosmic structure that lives in the vastness of space very close to us. In cosmic terms, Andromeda is considered ancient, having undergone a rich history of development and evolution with an estimated age of approximately 10 billion years. The idea that Andromeda originated billions of years ago by merging multiple smaller protogalaxies is an intriguing part of the galaxy's formation story. The magnificent Andromeda Galaxy that we see today was progressively formed through this process, which was accelerated by the force of gravity. Throughout cosmic timescales, galaxy formation and structure are largely shaped by the frequent occurrence of galactic mergers. Astronomers thought Andromeda was far larger than our own Milky Way galaxy for a very long time. This misperception was partially caused by the fact that Andromeda seems enormous when viewed from Earth. Nevertheless, new findings have caused scientists to re-evaluate these theories and update their estimations of Andromeda's mass. It is clear from current knowledge that the masses of the Milky Way and Andromeda are far closer than previously believed, underscoring the difficulties in precisely determining the masses of galaxies. Astronomers continue to disagree on Andromeda's exact size. Nevertheless, Andromeda is larger than the Milky Way, with a diameter of about 220,000 light-years. Because of its enormous size, Andromeda is a huge cosmic entity that occupies a large part of space. The difficulties in precisely determining the mass of galaxies highlight the difficulties in researching these enormous cosmic formations. Galaxies are complex systems, and the distribution and motions of stars, gas, dust, and dark matter within them are closely related to the mass of these systems. This calls for careful examination and advanced observational methods that were not possible until recently. A supermassive black hole powers the incredibly powerful active galactic nucleus of Andromeda, one of the galaxy's most intriguing features. Innovative phenomena within the nucleus, such as two spots of concentration where emissions are more strong than in the surrounding areas, have been revealed by observations made with sophisticated observatories such as the Hubble Space Telescope. These studies extend our knowledge of galactic nuclei and provide insight into the dynamic processes taking place at the center of Andromeda. Huge gravitational pull is exerted by the supermassive black hole at the center of the Andromeda Galaxy, whose mass is believed to be between 1.1 and 2.3 times 10 to the power of 8 solar masses, or roughly 110 to 230 million times that of the Sun. Supermassive black holes are thought to be ubiquitous objects in the centers of galaxies, such as the Milky Way, and their existence has a significant impact on the dynamics and evolution of these cosmic structures. An accretion disk is created around a supermassive black hole when matter, like as gas and stars, approach it too closely. The material spinning within this disk heats up and releases a powerful amount of radiation at different wavelengths, which adds to the galactic nucleus luminosity. Because of the special gravitational interactions that occur between the black hole and the surrounding stars, astronomers have observed a brighter point of concentration close to the central supermassive black hole in the Andromeda Galaxy. The supermassive black hole at the center of the Andromeda Galaxy pulls on nearby stars with such strength that it changes their orbits. These stars follow elliptical orbits that resemble planets in our solar system circling the Sun. Gravitational forces reach their peak around the perihelion, or point closest to the black hole, which causes stars to accelerate and become more densely crowded around the black hole. The brighter point of concentration seen in Andromeda's galactic core is a result of this concentration of stars and the radiation they generate. Apart from its huge black hole, Andromeda is rich in globular clusters, which are dense collections of stars revolving around the galactic center. The estimated total number of these clusters in Andromeda is 460. They provide important information about the cosmic history of the galaxy and its interactions with smaller galaxies spanning billions of years. These globular clusters' existence implies that Andromeda has actively engaged in galactic cannibalism, absorbing stars and other elements from smaller galactic neighbors that are subject to its gravitational pull. In addition, new findings and interpretations suggest that the Andromeda Galaxy may be undergoing a change from a common spiral galaxy to a somewhat uncommon kind called a ring galaxy. Circular or elliptical ring-like structures made of luminous young blue stars encircling a center region with comparatively less luminous matter are the hallmarks of ring galaxies. If verified, this shift would underscore the dynamic character of cosmic evolution and contribute to the galaxy's fascination. The two main forms of ring galaxies are O-type and P-type, named for their circular or elliptical ring-like features. P-type ring galaxies have off-center nuclei and more asymmetrical ring forms, whereas O-type ring galaxies have centrally situated nuclei and smooth, regular rings. About 1 in 10,000 galaxies are classed as ring galaxies, making them uncommon cosmic occurrences. There are two primary theories put out by astronomers to explain how ring galaxies develop. First, they may arise as a result of a galaxy or galaxies colliding. On the other hand, a ring-like structure may occur when a smaller galaxy passes through the core of a larger galaxy. The Cartwheel Galaxy, Galaxy NGC 20264, and ARP 147 are a few examples of ring galaxies that are believed to have originated through galactic collisions, demonstrating the complex interaction of cosmic dynamics. But what's happening right now is even more fascinating. According to scientific predictions, the Andromeda and Milky Way galaxies are headed toward collision and will eventually combine to form a new supergalaxy. Global media attention has been drawn to this enormous event, to the point where it has spawned humorous monikers such as Milkdromeda or Milkomeda. Even while these monikers might seem whimsical, there could be significant ramifications for humanity from this union. Stars, gas, and dust are drawn between the two galaxies during tidal interactions caused by the enormous gravitational forces between them as they get closer to one another. The galaxies will eventually overlap, wreaking havoc and ruin. Stars, gas clouds, and dust clouds from the two galaxies will interact and mix as the merger process goes on, possibly creating new star clusters and structures inside the newly combined galaxy. Where gas clouds collide and compress, the collision will cause bursts of star formation, forming new stellar nurseries. Significant repercussions of the merging process will also be felt on Earth. Changes in the solar system's environment may have an effect on Earth's climate and weather patterns, which may cause habitat disruptions, biodiversity shifts, and local extinctions. The distribution of plants and animal habitats may be impacted by worldwide variations in temperature, precipitation, and meteorological events. Moreover, Earth's atmosphere, which includes the ozone layer, may be impacted by an increase in cosmic radiation in the intergalactic region. This might have an impact on climate patterns and vital processes for plant and animal life. Thus, the merging of galaxies may have profound effects on earthly life, underscoring the relationship between cosmic occurrences and terrestrial ecosystems. The habitats of different species may change or become less favorable when climate and ecosystems change. Particular migratory patterns are essential to the survival, reproduction, and foraging of many animal species. The disruption of migration routes and timings resulting from alterations in temperature and ecosystems may present difficulties in locating food, water, and appropriate nesting locations. Changes in biodiversity within ecosystems may also result from altering habitats and the climate. Certain species would do well in the new environment, while others might find it difficult to adjust, which could result in local extinctions. There may be more competition for resources, and there may be new chances for some species to thrive in the altered habitats. Regrettably, changes to migration patterns and habitats can have a domino effect on the ecosystem as a whole, which may lead to the extinction of some species from particular areas or habitats. The Milky Way and Andromeda galaxies will not join overnight, despite the fact that these developments are alarming. It is estimated that the collision will start about 4 billion years from now, and that the merging process will take an additional 2 billion years to finish. It is anticipated that our Sun will have transformed into a red giant by then, making our solar system inhospitable well in advance of the galactic merger. In billions of years, if our species' offspring or other living forms still exist, they most likely won't look anything like us in terms of evolution. Our solar system may be absorbed into the new galactic structure or expelled into the intergalactic medium, depending on how it is disposed of inside the new supergalaxy. The likelihood that habitable planets will exist within the new galaxy structure will depend on how stable it is. Although liquid water is thought to be essential for the emergence and maintenance of life, planetary orbits and environmental factors may be impacted by interactions between stars and possible gravitational disruptions. The emergence of life in the new galaxy is expected to involve adaptation to its particular environment, which could lead to the emergence of diverse kinds of life that differ from those found on Earth. It's improbable, though, that modern humans could survive in this new galaxy unless they underwent substantial evolutionary modifications. The ability of creatures to adapt to the unique environmental circumstances and other elements will ultimately determine the course of life's evolution and sustainability in the new galaxy. Galaxies merging highlights the dynamic nature of the universe and the ongoing evolution of life within it, while also offering exciting opportunities for the formation of new forms of life.